Oh, and welcome back. You're, what you're seeing behind me is a rendition of the topics that we're going to be covering today, particularly two-dimensional geometry, where we're going to be talking about perimeters and areas, how to distinguish and determine those in a number of different settings. In order to start with our topics, the first thing we need to look at is the notion of a point in space. So if I make a small hole in that piece of cardboard, a hole is there, but it's hard to distinguish. It is much easier to identify that spot if I place and leave the push pin in, because it gives a larger mark. So whenever we plot points in space, particularly on a Cartesian or coordinate system, we generally make fairly large dots, so we're able to identify them. Um, but a dot takes up no space. When we have two dots in space, we can generally, the shortest distance, according to some approaches to geometry, is we have a distance. And distances are simply the difference in position between 2 points. Such 2 points can be marked off in terms of dowels, and this is a particular dowel. So is this, and each of these. So we have dowels of several different lengths, and it would likely be confusing if someone told you that a building is this many dowels far away, or this many dowels tall, when you've only ever experienced a dowel of this length, and they're dealing in dowels of this length. So you take this many dowels, or you go this many dowels, and you can't find what you're looking for, because you still have to go a bunch further. The same problems did exist back in the Greek era, and up until only a couple hundred years ago, when distances started to get standardized. These several dowels are 4-inch, 6-inch, and 12-inch long dowels. So 3 dowels of the short one is the same distance as 1 dowel of the long, or 1 dowel of the middle size is half the length of the long dowel. So we need 2 of these to go the same distance as 1 of these. So that is the length of a line, simply the distance between 2 points. And that line's distance or length doesn't change regardless of how it is positioned. So I can spin this around and the length doesn't change. That's one of the nice things about distance. The position and orientation doesn't affect its distance. So when we measure lengths, we're talking about perimeters. And when we're talking about perimeters, we're talking about the length of figures that have multiple sides. So this figure here is a quadrilateral. It is made up of 3 shapes and it has 4 sides. We have 2 triangles and a rectangle that make this up. In order to determine this perimeter of a figure that has a number of any number of straight sides, all we need to do is add the lengths of the four distinct sides. So the length of the top, the length of the bottom, and the length of each of these sides. When we want to figure out the area of other figures, such as the perimeter of circles, we use a notation called the circumference, and this blue dot can be, the edges of it can be considered as marking off a circumference. Also, whenever we're dealing with when we deal with the area of a two-dimensional shape, it is the amount of space inside the figure. So we have an inside here, an inside here, and an inside here. And if we ignore these purple verticals, the entire area in here is considered to be inside this trapezoid. A four-dimensional figure with only one pair of sides parallel is a trapezoid. So, to find the perimeter of a four-sided figure, we take side length 1 plus side length 2 plus side length 3 plus side length 4, and we have our perimeter. For a three-sided figure, like a triangle, we have side length 1 plus side length 2 plus side length 3 gives us a perimeter. Our circumference, or the distance around a circle, is given by 2 times the value of the number pi, approximately 3.14159, times the radius, with the radius being the distance from the center of a circle to its nearest edge. Twice the radius is our diameter, and our diameter is twice the radius, and it's the distance through the center of a circle from one edge of the circle to another. It is the longest chord possible in a circle, where a chord is any line that connects 2 points on a circle. Have you ever wondered why, for certain races in a track, during what you may watch during the Olympics or other times, the runners start at different positions? Well, the answer to that has to do with the circumference of the circular parts of the track. If you have a straight race, like a 100-meter dash or 100-meter sprint, everyone starts in a line and ends in the same line because their path is straight the whole time. When you have people running around a corner, they have to compensate for that because the lengths on the outside of the corner have larger radii. So they need to make sure that the paths they take are the same length, and to give the outer runners more fair time, their starting positions are further around the corner and will appear to be further up the track. So this guy out here with the blue hat runs around the outside and has further to go than someone running around the inside of the track. And let's try to figure out how much further one would have to go for the outer track as opposed for outer lane as opposed to an inner lane. So if the inner lane has a radius of, let's say, 10 meters, and we add 1 meter per lane, lane 1 has a radius of 10 meters. The radius of lane 2 is going to be. So we've determined the areas of our triangles as being 6 square inches and the area of a rectangle to be 24 square inches. And we're interested in verifying the area of our trapezoid. So as I said, the area of this trapezoid, made up of our orange sides, our blue sides, and our blue and orange side, we claimed before, is 18 inches squared. Using the formula 1/2 base 1 plus base 2 times our height. I told you before that the base 1 is 6 inches. But I told you before that base 2 is 9 inches. 6 plus 3, I forgot to add this other 3. So that should be 12 inches times a height of 4 inches. So we have 18 inches times 4 inches times 1/2 gives us 36 inches squared, which is the same as you get when you add the 3 small areas. So it is always good to go back and check your work. We've looked at the key ideas behind identifying points in space and how they're usually noted. Lengths between 2 points in a straight line, the circumference of a circle, and the perimeters and surface areas of triangles and rectangles and trapezoids. We haven't yet looked at the area of a circle. So let's take a look at that. Okay. So this circle here has a diameter of 4 units, a radius of 2 units, and to find our area of any circle, we're going to multiply its radius times pi times its radius squared. And what we arrive at is, in this case, our radius is 2 units, pi times 4 units squared. When I drop this into a calculator, I get 12.566 units squared. Okay, that seems a bit too many because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 dots showing. Okay. But that doesn't count in the region added here and lost out on the sides. Okay. So this circle of 2 units radius has an area of 12.566 square units. Our rectangular football field that we said is 140 meters long by 6 meters wide. Let's figure out how many meters that would be using the area formula for a rectangle. Our length, we said, is 140 meters. Our width, we said, was 60 meters. So we're going to multiply 140 times 60, and we get 8,400 square meters, of which the area of the field itself is going to be 100 meters by 60 meters, or 6,000 meters. And the area of each end zone is going to be 40 meters times 60 meters, or 2,400 square meters. So we took a look at the area and perimeter of a number of quadrilaterals and triangles, and the circumference and area of several different circles and circular figures. These form the basic ideas used in most geometry that we run into every day.